I'm a physicist, and what I do is I'm an experimental physicist. I build devices in a lab, and I try to answer physics questions, fundamental questions that might help inform us about how a variety of things happen in nature. The physics questions I'm interested in are all inspired by two different directions. One is how might we make a star on Earth to produce fusion energy for mankind? And this is a long-term goal for humanity. Fusion represents the biggest source of energy within the planet. If you look at the amount of light atoms that could be turned into heavier atoms through nuclear fusion. It's a process that happens in stars. It powers the universe. If we could make this happen on Earth, we would have a clean, abundant energy source. And so a lot of my research has been in this area. The other area is inspired by what we're learning today from this spectacular generation of telescopes that we have. We're really in a golden age in astronomy, and I'm not an astronomer, but astronomy now has a collection of space telescopes, for example, that are able to observe the universe with the best instruments we've ever had, looking across an enormous spectral range. So we can look at the universe in the optical, we can look at the universe through radio waves, we can look at the X-ray emission coming from the universe, and we can see different pictures. And the pictures we get back are just completely awe-inspiring, and they provide me with questions that I might answer in the lab. And that's kind of the gist of what inspires my research. So I'm a physicist, an experimental physicist, but I'm also a plasma physicist. So plasma is a state of matter that is very, very hot ionized gas. So normally we think about states of matter in terms of solids are a state of matter, a liquid. If you heat a solid, the particles gain enough energy to turn into a liquid. If you heat a liquid, it turns into a gas. And then if you heat a gas to very high temperatures, eventually the atoms break up into their constituents. You get a gas, which is a mixture of the electrons which were bound to the atoms, but now they're free to move, and the core of the atoms, we call them ions. They're much heavier. Those are the protons and neutrons which were in the center of the atoms. Those form a gas of electrically charged particles. And so you have these negatively charged electrons and these positively charged protons, say, moving around. Those create electric and magnetic fields and an enormous range of new phenomena that doesn't happen in simple gases or solids or liquids. I build things in the lab that are usually some sort of vacuum vessel. We build a tank, a stainless steel tank. We evacuate it. We take all the gas out of it. And then we inject a little tiny bit of the gas we want to look at into it. Maybe we'll shoot microwaves in. We'll make a plasma, so we can heat a little bit of gas to very high temperatures, hundreds of thousands, millions of degrees, and we can make the plasma in a certain way. I realized that we could do things differently. We invented a new technique for confining plasmas without magnetic fields, and then devised a mechanism for stirring the plasma. So it's not possible to take a plasma, which is a very, very diffuse gas, and put a paddle into it and stir it. We had to invent a technique for doing that involves sort of electrical motors of some sort. And now we're studying, we're trying to make plasmas that are stirred in the way that the sun is stirred, that are stirred in the way that the core of the Earth flows, and study how magnetic fields are generated from that. So my research took off from one direction, which was the application of developing fusion energy as an energy source, and now is more focused on studying these astrophysical phenomena.
Would you be able to go on any of the orbiting space stations and do any of your experiments up in space?
Me and my colleagues regularly look at data from spacecraft that are measuring the plasma just outside of the Earth's atmosphere, if you go into the space station or beyond, with things like Voyager and the other space missions that NASA sends out. What they're measuring they're measuring plasma physics phenomena. The things that can be measured by the spacecraft which explore the solar system are the plasma physics things that happen out there. And so one of the things that's most exciting to me is that in about 2 years we're going to be launching a special mission which will launch a satellite that will get as close to the sun as we've ever gone, and it hopes it'll go to about 10 solar radii away from the center of the sun, and by measuring that region, we'll learn a lot about the plasma physics of the sun that we haven't been able to study before. So yes, so plasma physics is not only in the lab, it's not only in astrophysics, just by observing with using telescopes, but it also involves putting space instruments into flight and measuring what's happening in situ.
What's the practical application of the work you do?
Some people say that the purpose of physicists is to turn coffee into papers, and so a lot of what I do is very much curiosity driven, and I think it's and I have a very applied side to what I do when I study nuclear fusion research. We hope to build an energy source which is like the sun, build a star on Earth that can create fusion power for power generation. So that's a highly applied application of plasma physics. And on the other side of the coin is the curiosity-driven research that I do, which is inspired by what we see in nature and just trying to understand it. So that's not necessarily an application. We don't have an application, a commercial application, say, but the curiosity itself drives us in directions that we don't know where it will take us. When the transistor was invented, it wasn't clear what its purpose was going to be. When the laser was invented, it wasn't clear what it would lead to. And those things have led to very interesting commercial applications, but only 20 or 30 or 40 years later. And so basic research is fundamental to leading to those advances 50 years down the road.
As you look to the next 10 to 20 years, what excites you the most? What do you think might be the groundbreaking discoveries?
So I guess I'm going to answer this question not in my own field. I personally think that the brain and understanding what a thought is the most interesting, one of the most interesting intellectual questions facing mankind. So cognitive sciences and the idea that somehow we can figure out what a thought is and piece that together is I think that will be something that gets cracked, and it's going to be very multidisciplinary. It's going to be some team of mathematicians and computer scientists and biologists and neurobiologists coming together to figure that out. And if I were starting again, I would probably be a neurobiologist or neurophysicist. But I think astrophysics is a close second, or maybe beats it out. So.